Okay, let's unpack this. Welcome to the deep dive. We're plunging into the intricate, fascinating world of how our digital lives are actually put together.
It's pretty amazing when you think about it.
Totally. Today, our mission is a real deep dive into what it genuinely means to design software systems that aren't just, functional, but also incredibly scalable, super reliable, and really efficient.
Especially now, right? With everything being so complex and distributed.
Exactly. It's powering almost everything you interact with online, often silently. We've pulled together a bunch of expert insights, some real-world case studies for our sources today.
Yeah, some great stuff to look at.
And the goal, our ambitious goal, is to equip you, our listener, with the essential knowledge, the sort of conceptual tools, to really grasp the engineering humming beneath the surface of the digital world you navigate every single day.
It's remarkable, isn't it, how central system design is now? What's fascinating here is that it's this invisible architect, kind of the silent orchestrator behind basically every digital thing you do.
Like checking social media.
Yeah, or streaming a movie. It directly impacts your daily experience, often without you even noticing. It's not just what these systems do.
It's how they do it.
Exactly. How they manage it so effectively, so consistently, and at these, well, massive scales we see today. And as software just keeps getting more complex, more
Yeah, it's
distributed,
relentless.
it really is. The ability to actually design and build these robust, high-performing systems isn't just nice to have anymore. It's like the absolute cornerstone of digital innovation and reliability.
So let's lay some groundwork. When we talk about system design for software, what are we really talking about?
Good question. At its core, it's this whole process, often iterative, of defining the architecture.
The big picture.
Right, specifying the components, their interfaces, figuring out all the critical characteristics the system needs, and why, to meet the requirements.
It's like the blueprint, right? Before you build the house.
Perfect analogy.
Yeah.
The detailed blueprint before any construction starts. It's all about careful planning upfront.
And crucially, we're usually not talking about just one program on one computer.
Oh, rarely these days. We're almost always diving into these incredibly complex distributed systems. Networks of computers, linked up, maybe spread across continents, all working together.
Wow.
Yeah, the blueprint idea really nails it. It's about taking those, sometimes fuzzy user requirements or business needs and turning them into a concrete, structured plan.
Actionable.
Totally actionable. And that plan becomes the bedrock, the foundation for successful development. If you skip that rigorous design, you're basically flying blind trying to build something complex.
Recipe for disaster.
Pretty much. High risk of inefficiency, instability, maybe total failure. And generally we think about design on two levels. There's high-level system design.
The 30,000-foot view.
Exactly. The overall architecture, data flow, how you'll handle scale, fault tolerance, big boxes, arrows. Then there's low-level system design.
Getting into the weeds.
Down in the weeds. Implementation details, specific components, could be choosing algorithms, data structures, defining the exact APIs for a service.
And you end up with design documents.
Right. Detailed design docs are produced throughout. They're those invaluable blueprints guiding the engineers during implementation.
That high-level versus low-level distinction, that's key. Okay, with that foundation, let's pivot. Let's talk about the essential attributes, the core characteristics that underpin modern system design. These aren't just buzzwords. They're critical things you have to consider for any robust, scalable system today.
Absolutely fundamental.
First up, consistency. Simple terms. It means your data is always valid and updates are reflected uniformly across the whole system.
Right. So once a change is made, any later read gets that latest correct version.
Sounds simple, but I bet it's not in distributed systems.
Oh, it's a huge challenge. Let's use that classic hotel room booking example. It illustrates it really well.
Okay.
Imagine user 1 books room R1. The write hits DB1 first. Now, for consistency, that booking needs to get copied, replicated to DB2 and DB3.
But that takes time, network lag.
Exactly. It's not instant. The network latency, system load. And while that replication is happening, say user 2 checks for that same room, R1.
Uh-oh.
Oh, is right. Whether user 2 sees available or booked depends entirely on which database node their request hits. If it hits DB2 before the update arrives.
They see stale data. They think the room's free.
Precisely. They might try to book it too. This highlights a core challenge, keeping data perfectly synchronized across geographically spread out systems. It's a fundamental trade-off.
Okay, next, availability. This sounds like what it is. The system stays operational, accessible, even when parts of it, well, fail, which they do.
They inevitably do. Availability is all about uptime. We measure it in nines.
Like 5 nines.
Right. So 99.9% availability, 3 nines, means about 8.76 hours of downtime per year. Manageable for something.
But 5 nines, 99.999%.
That's a huge leap. It gets you down to about 5 minutes of downtime per year, but getting there,
Yeah.
exponentially harder.
Why so much harder?
Because you need insane levels of redundancy, super sophisticated fault detection, automated failover, the ability to do maintenance without any downtime. It gets expensive fast.
And companies commit to this.
Often, yes. Formal commitments are in service level agreements, SLAs, for customers. Internal targets are SLOs, service level objectives, and achieving high availability. It boils down to strategies like redundancy duplicating components and fault tolerance, designing the system to handle failures gracefully.
Which leads us right into partition tolerance. This is about what happens when parts of your distributed system just can't talk to each other because the network breaks. A network partition.
This is absolutely critical. It underscores how fragile network connections can be at scale. Imagine your DB2 node gets cut off from DB1 and DB3. Maybe a router fails, someone trips over a cable.
Or just a configuration mistake.
Happens all the time. Now, any new writes going to DB1 or DB3, they can't update DB2.
So if my request hits DB2,
You get stale data. You're completely unaware of the latest changes happening elsewhere. And network partitions aren't theoretical edge cases. They will happen in large systems.
guaranteed.
Pretty much guarantees. Hardware fails, software has bugs, networks go down for maintenance. Designing systems that can still function, or at least function predictably despite these partitions, that's crucial for reliability.
Then there's latency. That's the delay, right? Between asking for something and getting it back. And here's where it gets really interesting. Because nobody likes waiting. You don't like waiting.
You're absolutely right. Low latency isn't just tech bragging rights. It's key to a good user experience. We use several clever tricks.
Like what?
Data localization is huge. Get the data physically closer to the user.
How?
Replication strategies, edge computing processing data near where it's generated, and content delivery networks, CDNs, which cache static stuff like images and videos globally.
So the data travels less distance.
Exactly. Another big one is asynchronous communication. Instead of waiting for a reply, components use message queues or event-driven patterns.
They fire and forget.
Sort of.
Kind of. It decouples things, allows parallel work, feels faster. And finally, constant performance tuning. Optimizing configurations, database queries, algorithms always shaving off milliseconds.
Next up, durability. This sounds important. It's the guarantee that once data is saved, it stays saved forever, even if the system crashes.
Durability is non-negotiable for critical data. Your bank balance, medical records, family photos, you expect that data to persist.
So how do we ensure that?
Vigorous replication across multiple nodes is key. If one node dies, the data exists elsewhere.
Makes sense.
And robust, often geographically separate backup systems are vital for long-term storage and disaster recovery, especially for finance, healthcare, or continuous services like social media.
Are there trade-offs?
Sometimes, yes. Achieving super high durability might occasionally conflict with immediate consistency or even availability during certain failure modes, as the system might prioritize saving the data securely over letting you access it right now. And closely related is reliability. What does that really mean in these complex distributed environments?
Reliability is more than just uptime. It means the system consistently provides its intended functionality despite all sorts of failures.
Hardware failures, network glitches.
Software bugs, human error, you name it. A truly reliable system ensures data and services are consistently available, accessible, and delivered promptly, even when things go wrong. It's about predictable, correct behavior under stress.
Which flows nicely into fault tolerance. This is how systems keep running correctly even when parts fail, the ability to take a hit and keep going.
Fault tolerance is the heart of resilience. Key techniques: redundancy, duplicating critical components or data. If one fails, a backup takes over seamlessly.
Like having a spare tire.
Exactly. Replication is similar. Multiple identical copies of data or services, maybe in different data centers. If one center goes offline, the service continues elsewhere. And finally, robust error detection and recovery. Things like heart beating, where components signal they're alive, sophisticated monitoring for anomalies, and automated health checks that can trigger self-healing. The system tries to fix itself.
The last but definitely not least for these core attributes, scalability. This is the big one for growing apps. The system's ability to handle more load, more users, more data, more requests without slowing down.
Scalability is often the reason we build distributed systems in the first place. There are two main ways to scale. First, vertical scaling or scaling up.
Bigger machine.
Yep. Add more CPU, RAM, faster disks to an existing server. It's simple, easier to manage in some ways.
Yeah.
Data consistency is straightforward,
But
but there are limits. Hardware only gets so big. It's a single point of failure risk. If that one beefy server dies, you're down. And those big servers get really expensive.
the other way.
Horizontal scaling, scaling up. Add more servers to share the load, like building a fleet instead of one giant ship. Databases often call this sharding. Lots. Higher fault tolerance, one server fails, others pick up the slack. No real hardware limits, just add more commodity machines, and it's usually more cost-effective using standard hardware. This is how most massive web services scale today. Hashtag key theorems shaping distributed systems.
Okay, we've got the core attributes down. Now let's get into some of the theoretical frameworks that really guide architects in making smart decisions. These aren't just academic exercises. They directly impact how real systems get built.
Absolutely. They provide crucial mental models for understanding the inherent trade-offs.
First up, the classic, the CAP theorem. It lays out that fundamental tension between consistency, availability, and partition tolerance.
Right. The CAP theorem, often credited to Eric Brewer, it basically says that when a network partition happens, and remember, we said partitions will have, you have to choose. You can guarantee consistency or you can guarantee availability.
But not both.
Not both at the same time during the partition. That's the critical insight. Since partitions are inevitable, the real decision is, what do you prioritize when the network breaks? Traditional relational databases often choose CP consistency and partition tolerance. They'd rather be temporarily unavailable or reject a transaction than risk serving inconsistent data. Think banking accuracy is king.
Okay.
But other systems, maybe social media feeds or content sites, might lean towards AP availability and partition tolerance. They prioritize staying online, even if it means some users see slightly delayed or eventually consistent data for a short time. Being accessible is more important in that context.
But wait, it gets even more nuanced, right?
Yeah.
Because CAP mainly focuses on what happens during a partition. Here's where it gets really interesting. The PALC theorem. It's like KIP's more detailed cousin.
That's a great way to put it. PALC builds on TAP and adds another crucial layer. It says, okay, partition happens. You choose between availability and consistency. That's the CIP part. But else meaning when the system is running normally, without a partition, you still face a trade-off between latency and consistency.
So even when things are fine, there's a choice.
Exactly. Do you want super high immediate consistency for every write, which might mean higher latency because nodes have to coordinate more? Or do you want lower latency, faster responses, accepting that data might become consistent eventually across all nodes?
But it's a constant balancing act.
Always. PACE-LC forces architects to think about this trade-off during normal operation, not just during failures. A real-time game might favor L, low latency, over C, while online banking favors C, strong consistency, over L.
Beyond these trade-offs, how do all these separate computers in a distributed system actually agree on something? Like, agree on a single value or make a decision together, especially when failures can happen? This is where consensus algorithms like Paxos and Raft come in.
These algorithms are the bedrock of fault-tolerant distributed systems. They solve the problem of getting multiple nodes to agree reliably. Let's start with Paxos.
The famous one by Leslie Lamport.
The very same, from 1990. Paxos is powerful, known for being complex, but it enables nodes to agree on a single value data, a decision even with failures and network delays. It involves rounds of communication with proposers suggesting values and acceptors voting. You need a majority to commit a value.
Complex to implement, I hear.
Historically, yes. Getting all of the edge cases right is tricky, which led to Raft.
A simpler alternative.
Introduced in 2013, Raft was explicitly designed for understandability and ease of implementation. It breaks consensus into three parts: leader election, log replication, making sure everyone has the same history of commands, and safety, ensuring correctness.
How is it simpler?
A key difference is Raft uses a designated leader to manage things, which simplifies coordination compared to Paxos's more peer-to-peer approach. But Raft still has challenges, like making sure the leader is always available and scaling overhead as the cluster grows. Both are foundational for systems needing strong consistency, like distributed databases.
And to really hammer home the difficulty of agreement when things might be unreliable or even malicious, there's the Byzantine generals problem, BGP. A classic thought experiment.
It's a fantastic illustration. Imagine generals surrounding a city. They need to agree, attack or retreat. But some generals might be traitors, sending conflicting messages.
how do the loyal generals agree on the same plan despite the traitors?
That's the core challenge. How do you get reliable consensus when some components might be faulty or actively adversarial? This is super relevant for things like blockchain.
Solutions.
Often involve voting algorithms. If fewer than one-third of the generals are traitors, the loyal ones can reach consensus by requiring a two-thirds majority vote, or multi-round signing, where proposals are cryptographically signed, making it possible to identify traitors who deviate. It really shows the depth of complexity in building truly trustworthy distributed systems, especially when you have to assume some actors might be malicious.
Okay, we've covered the core ideas, the theories. Now let's get practical. Let's talk about the actual components, the building blocks, at the heart of almost everything. Data storage. Databases, key value stores, they're the foundation, right? But not all are the same.
Absolute critical point. Databases are how we systematically store, organize, and retrieve huge amounts of information. They're the memory, the knowledge base, and yeah, the landscape is pretty much split into two main camps, relational and NoSQL.
Let's start with relational, the SQL databases.
Right. Think structured tables, rows, columns, strict relationships between tables enforced by schemas. They use SQL, structured query language.
What are the big advantages?
Referential integrity reduces data redundancy, ensures
sure.
quality, robust security features, and crucially, native support for ACG transactions.
ACD, remind us.
Economicity, all or nothing for a transaction. Consistency, database goes from one valid state to another. Isolation, concurrent transactions don't interfere. Durability, once committed, it's permanent.
Makes them great for finance, things needing strong guarantees.
Exactly. But they have downsides too. Complex joins across many tables can get slow at scale. They could be memory hogs. And scaling them horizontally is notoriously hard. Usually you scale vertically, which gets expensive and hits limits.
So the alternative emerged. NoSQL databases.
For different kinds of problems, right?
Precisely. Not only SQL databases were designed specifically for challenges where SQL struggled. Massive scale, needing flexible schemas, handling unstructured data.
What are their strengths?
They handle huge volumes of data well. They're built for cost-effective horizontal scaling, just add more servers. And they adapt easily to changing data structures without rigid schemas up front. Big win for agile development.
The trade-off.
Usually less emphasis on strong, immediate consistency. They often favor eventual consistency for better availability and partition tolerance. Think CAP theorem again. And you need careful data modeling and indexing for performance.
And there are different types of NoSQL. Oh yeah, several flavors. Key value stores are the simplest. Think Redis, Memcache, DynamoDB. They just map unique keys to values, like a giant distributed dictionary. Super fast for simple get and put operations. We talk about R and W read and write quorums to tune consistency.
Okay, what else?
Column family databases, like HBase or Cassandra, often called wide column stores. They excel at scale, high throughput for reads and writes, great for time series data, logs, analytics.
And graph databases?
Graph-based databases, Neo4j, Amazon Neptune, designed specifically for complex relationships. Data is nodes and edges with properties. Super efficient for traversing connections, saying social networks, friends of friends, recommendation engines, fraud detection. They use special query languages like Cypher.
So with all this diversity, especially in distributed stores like Key Value, how do we keep data safe and available? How does data replication and fault tolerance work there?
Great question. It gets down to practical strategies. For data duplication, two main models, primary, secondary. One primary node handles all writes, then replicates to read-only secondaries. Simple consistency, but the primary is a single point of failure.
And the other model?
Peer-to-peer. All nodes or peers can handle reads, writes, replicate among themselves. More resilient, but replicating to every node in a huge cluster is inefficient. So usually you replicate to a smaller configured number of nodes, like N3 or NF5.
Okay, and handling failures. Temporary ones first.
For temporary failures, like a node rebooting, we often use sloppy quorum and hinted handoff. If the node that should get the write is temporarily down, the request goes to the next healthy node on a preference list.
Like a backup receiver.
Exactly. That node processes the request, but includes a hint metadata saying who the write was originally for. When the original node comes back online, the data is automatically handed back. This keeps things available without waiting.
Clever. What about permanent failures? Node dies completely.
For permanent failures, Merkle trees are ingenious. They're hash trees. You hash individual key values at the leaves, then parent nodes hash their children's hashes all the way up.
How does that help?
It makes finding discrepancies between replicas super efficient. Instead of comparing all the data, nodes just exchange the hash values of branches in their Merkle trees. If hashes don't match, you instantly know which part of the data is out of sync, drastically reducing the data needed for repair. Much faster healing.
These are some serious behind-the-scenes mechanisms. Speaking of unsung heroes, let's shift to data delivery and management. Things like DNS, load balancers, and application gateways. These are working constantly, directing traffic, making sure your online stuff runs smoothly, but you probably don't even think about them.
Totally essential, yet often invisible. The absolute foundation is the domain name system, DNS, the Internet's phone book.
Translating names to numbers.
Exactly. Human-readable names like www.thedeepdive.com to machine-readable IP addresses like 192.10.0.2.10.1. Your browser needs that IP to connect. It uses a global hierarchical system root servers, tldservers.com.org, then authoritative servers for the specific domain.
How does a lookup happen?
Two main ways for DNS querying. Iterative. Your resolver asks the root, gets a hint, asks the TLD, gets another hint, and so on, doing the work itself. Recursive, your resolver asks one server, and that server does all the legwork to find the final answer and returns it.
And DNS needs to be fast and reliable, too.
Definitely. Caching is key for DNS scalability and reliability. Records get cached everywhere, your browser, your OS, your local network server, your ISP's resolver. This massively cuts down response time and reduces load on the core DNS servers.
So DNS finds the right address, but then how do we stop one server from getting swamped with traffic? That's load balancing, right? To spread the work.
Precisely. Load balancers are vital for high-traffic sites. They sit in front of your servers and distribute incoming requests intelligently across them. Prevents bottlenecks, optimizes resource use, improves response times, boosts reliability.
Can the load balancer itself fail?
Good point. It can be a single point of failure. So for high redundancy, you often have a second passive load balancer ready to take over instantly if the active one hiccups.
How do they decide where to send traffic? Algorithms?
Yep, various algorithms. Simple ones like round robin or smarter dynamic ones looking at server load, response times. We also talk about stateful versus stateless. Stateful ones remember which server you were talking to for sticky sessions. Stateless ones don't. They're often faster, more scalable.
And they work at different network layers.
Right. OSI model layers. Layer 4 looks at IP port.
Mm-hmm.
Layer 7 application layer is smarter. Can look at HTTP headers, URLs, cookies to make routing decisions.
How do you deploy them? Hardware, software?
All of the above. Hardware appliances, flexible software load balancers, or increasingly, cloud load balancers as a service, LBS. Cloud ones offer easy scaling, pay-as-you-go, often global traffic management.
Going beyond just spreading traffic, we get even smarter with application gateways, often just called API gateways, like an intelligent front door.
Exactly. An API gateway sits between clients and your backend services, acting as a smart intermediary. It does way more than basic load balancing.
Like what?
Intelligent routing, security enforcement, authentication, authorization, request response modification, rate limiting, caching, analytics, handling API versioning. They're super important for microservices architectures.
Because you have lots of little services.
Tons of them. And the API gateway provides that single unified entry point for all incoming API traffic. It centralizes cross-cutting concerns like security and monitoring, simplifying the backend services themselves.
Okay, let's unpack this. With all this communication, data storage, how are systems so fast, serving millions of requests? Often, the secret sauce is caching.
Caching is absolutely fundamental, maybe one of the most impactful optimizations. It's basically storing temporary copies of frequently accessed data somewhere faster, somewhere closer.
Right.
To reduce the time, the resources, the network calls needed to get that info from the original slower source, like a database.
Key ideas: cache hit, cache miss.
Right. Cache hit. Data's in the cache, super fast retrieval, cache miss. Data's not there, got to go fetch it from the source. Then you usually put it in the cache for next time.
And when apps get big, you need distributed caching.
Exactly. When you scale across many servers or data centers, instead of each server having its own little cache, you use a network of cache nodes working together as one big caching layer.
Benefits.
Huge benefits. Better performance, faster responses, reduced load on your databases, often the bottleneck, easier scalability because the cache scales independently, better fault tolerance, even cost savings, fewer expensive database queries. Definitely challenges. Cache staleness is a big one, keeping the cache synchronized with the original data. Data partitioning, spreading data evenly across cache nodes, data consistency, and cache invalidation, knowing when to remove or update old data. That's notoriously hard.
So when designing a distributed cache, how do you decide what to keep? Eviction policies.
Right, you need a strategy for when the cache gets full. A very common one is least recently used, LRU.
How does LRU work?
You typically use two structures,
How?
a doubly linked list to track the order of use, most recent at the front, least at the back, and a hash map for fast lookups by key.
So if I read something
If it's a cache hit, you grab it from the hash map, then move its node to the front of the list, making it most recently used.
and a miss,
Cache miss, fetch from the source, add it to the hash map in the front of the list. The cache is full. You kick out the item at the back of the list, the least recently used one. The idea to keep the data you're most likely to need again soon.
makes sense. And where do you put the cache? With the app or separate?
Good question. Co-located versus standalone cache. A co-located cache runs on the same server as the application. Advantage? Super low latency, no network hop. Disadvantage? Scales with the app, shares resources.
And standalone.
Standalone cache is its own separate cluster of servers. Advantage, scales independently, handles higher load. Disadvantage, more infrastructure, potential network latency between app and cache. Choice depends on the specific needs.
Popular cache solutions. I hear Redis and Memcached a lot.
Those are the big two. Redis is incredibly versatile. It's an in-memory data store, acts as a cache, database, message broker. Its strength is supporting various data structures, strings, hashes, lists, sets, sorted sets. It scales horizontally, has persistence options, used for everything from web caching to real-time analytics.
And Memcached.
Memcached is simpler, lighter weight, purely an in-memory key-value store designed specifically for fast object caching. Great performance for simple data types, also distributed.
How to choose.
Redis is generally more versatile if you need richer data structures or persistence. Memcached is simpler if you just need fast, basic, ephemeral caching. Depends on your application's needs.
Okay, storing data fast, retrieving it fast. But how do different parts of a huge system talk reliably without, waiting for each other, falling over, especially when they're decoupled? This sounds like asynchronous communication and messaging systems.
Absolutely. Messaging is the glue in modern distributed systems.
Hmm.
We've moved from monolithic apps where everything talks directly to microservices where services are decoupled and communicate mainly via message passing.
Why is that better?
Makes systems more resilient, scalable, easier to develop and deploy independently.
Let's start with distributed queues.
Okay, a distributed queue is just a queue spread across multiple servers. It stores and forwards messages, usually used when message order matters, or when only one consumer should process each message.
What are the advantages?
Load management, they act as buffers for message bursts. Decoupling producers and consumers don't need to know about each other. And reliability built-in read delivery if a consumer fails.
Delivery guarantees. Like, messages definitely arrive.
Different semantics.
Yeah.
At least once means it will arrive, maybe more than once. Exactly once is harder. Guarantees unique. Ordered delivery often needs special FIFO queues. And dead letter queues catch messages that repeatedly fail processing.
What about pub subsystems? Sounds different.
It's a broadcast pattern. Publishers send messages to named topics. Multiple independent subscribers can listen to those topics and receive the messages.
So one message goes to many listeners.
Exactly. Think of a news alert system. One publisher sends to the breaking news topic, and many subscribers get it. Key ideas are managing topics, managing subscribers, and efficiently routing messages. This is called fan-out.
Popular platforms for this? Kafka.
Apache Kafka is huge. A distributed streaming platform built for high-throughput, real-time data feeds. It's durable, fast, scalable, handles both pub-sub and queue patterns. Core ideas are topics, producers, consumers. It also has Kafka Streams for building stream processing apps.
Any others?
Amazon Kinesis is a popular managed service in AWS, similar capabilities. Overall, these messaging systems are absolutely essential for building robust, scalable, real-time distributed systems.
We've covered internal communication really well. Now, how does the outside world or even other internal services talk to these systems? APIs, application programming interfaces, they're the bridges. But how do we design how they talk?
API design is crucial. It defines the contract for interaction. Two dominant styles today are REST APIs and gRPC APIs.
Let's start with REST. That's everywhere.
REST, representational state transfer, is built around resources identified by URIs. You use standard HTTP methods, GET, POST, PUT, DELETE for CRUD operations. Key feature, statelessness. Each request has all the info. The server doesn't remember context. Simple, flexible, good caching support via HTTP, decouples client and server well.
Cons.
It can lead to overfetching, getting more data than you need, or needing multiple round trips for complex stuff.
Okay, and gRPC.
gRPC, Google Remote Procedure Call, is high performance, open source, uses HTTP2. It's function-centric, not data-centric like REST. You define services and methods clients call.
How does it send data?
Uses protocol buffers, protobuf, for defining interfaces and serializing data. It's binary, much more efficient and faster than JSON used in REST.
So pros are speed and efficiency.
Highly efficient, lower payload, faster, great for internal microservice communication.
Cons.
More complex setup maybe, debugging binary formats is harder, changes can require coordinated deployments.
With all these APIs connecting things, API security must be critical. Data breaches are constant news. How do we protect these bridges?
Non-negotiable.
No.
First, understand authentication versus authorization. Authentication is, who are you? Verifying identity, login. Authorizations, are you allowed to do that? Checking permissions.
How do we manage that?
OF 2.0 is the standard for delegated authorization. Lets an app access your resources without getting your password. Think login with Google. OpenID Connect, OIDC, builds on OF as identity verification, often using JWTs, JSON Web Tokens.
And single sign-on. SSO.
SSO lets you log in once to an identity provider, IDP, and access multiple apps without logging in again. Huge usability win.
Then there's rate limiting. So what does this all mean? Why is this essential for keeping services stable?
Rate limiting is a vital defense. It restricts how many requests a client can make in a time window. Essential to prevent abuse, stop denial of service attacks, ensure fair usage, and manage server resources.
How does it work? Different algorithms.
Several common algorithms. Fixed window counter.simple, but allows bursts at window edges.
Yeah.
Sliding window log, tracks every request timestamp, smoother but memory intensive. Then there's the token bucket. Imagine a bucket getting tokens at a steady rate. Requests consume tokens. If the bucket's empty, the request is rejected. Good for handling bursts up to the bucket size.
Then leaky bucket?
Leaky bucket. Requests fill a queue, the bucket, processed at a fixed rate, leaking out. Smooths bursts to a consistent output rate. Good for ensuring steady processing.
Doing this across many servers is hard. Distributed rate limiting.
Big challenges. Synchronization, making sure all nodes respect the global limit, needs sticky sessions or a central store like Redis. And race conditions, multiple requests updating the counter at once, need atomic operators for updates to be safe.
What happens if you exceed the limit?
Typically, the API returns an HTTP 429 too many requests error. And underpinning all secure communication online. Transport layer security, TLS, which gives us HTTPS.
Encrypting the connection.
Exactly. Creates a secure tunnel between you and the server. Ensures privacy, no eavesdropping, integrity, no tampering, and authentication, verifying the server. Absolutely vital.
Okay, APIs, security. That's how things talk and stay safe. But with these huge distributed systems, how do you actually know what's going on inside? How do you watch everything, spot problems? This sounds like observability.
Exactly. Observability is key to understanding a complex system's internal state, just by looking at its outputs. It's about being able to ask new questions without deploying new code. It relies on three main pillars:
Fair.
logging, metrics, and distributed tracing.
Let's start with logging, recording events.
Yep. Logs capture what happened when, providing context for debugging, finding patterns and checking issues. In distributed systems, you absolutely need a centralized logging infrastructure.
Nice.
To gather logs from all services, all machines, into one place for analysis. Gives you a holistic view. Tools like Logstash, Fluent, and Northeast help manage this.
Second pillar, metrics. These are numbers, right?
Quantifiable measures over time. CPU usage, memory, network I/O, error rates, request latencies, queue sizes, the system's vital signs. What's fascinating here is metrics are often the first sign something's wrong.
How do you use them?
Track trends, set thresholds, spot anomalies. Best practice is monitoring key indicators like errors and latencies for every service. Visualize them with dashboards. Grafana is popular for quick insights.
And alerting. That builds on metrics.
Right. Proactive notifications when metrics cross critical thresholds, like error rate too high, latency spiking. Alerts go out via email, Slack, PagerDuty, so teams can react fast before users are heavily impacted.
Okay, the third pillar sounds complex. How do you follow a single request as it bounces across dozens of services? Distributed tracing.
It solves exactly that problem. Distributed tracing tracks one request's entire journey across multiple services and machines. Each step, a database call, an API call, is a span. The whole journey, the collection of spans, is a trace.
What does that give you?
A complete picture. You see which services were involved, in what order, how long each step took, where errors occurred, lets you pinpoint bottlenecks, find root causes of failures incredibly quickly. Tools like OpenTelemetry, Jaeger, Zip can help implement this. Consistent context propagation, passing a trace ID along is key.
We've covered theory, building blocks, observability. Now let's see how it all comes together. Let's look at real-world problems and how these concepts solve them. Starting with challenge 1, generating unique IDs at scale, like for a URL shortener.
Exactly. You need IDs that are unique, maybe numerical, maybe 64-bit, ideally time-ordered, and you need to generate them really fast without a bottleneck.
How?
Several ways. Multi-master replication with different auto-increment offsets. Complex. UEIDs are globally unique, but not ordered or numerical, and bigger at 228-bit. A ticket server like Flickr used centralized auto-increment DB. Simple, but single point of failure, bottleneck.
What's better?
The Twitter Snowflake-like approach is very popular. It generates unique, time-ordered 64-bit IDs decentrally. Combines a timestamp, a machine ID, and a sequence number. Avoids bottlenecks. IDs sort by time.
Or range server.
A range server hands out blocks of IDs to worker servers, reducing load on the central service. For a URL shortener, you take that generated ID, convert it to base 62, 09, AZ, to get a short string like 7 characters. Gives you trillions of possibilities. Then decide. 301 permanent redirect cached, or 302 temporary, not cached, destination changeable.
Fascinating. Okay, challenge 2. Proximity search. Finding nearby things like restaurants near you. A simple SQL query in latitude-longitude is slow, right?
Terribly inefficient.
Yep.
Standard database indexes aren't great for 2D spatial queries. You need special structures, like a quad tree.
How does that work?
Recursively divides the 2D space into 4 quadrants. Nodes store spatial info. Very efficient for range searches. Find everything in this box. Often used in memory, good for frequent updates like tracking vehicles.
Another
Geohashing represents a lat long as a short alphanumeric string. Longer string means more precision. Nearby locations have similar geohash prefixes, so you can do proximity searches using standard string prefix matching in a database. Simpler to store and share. Both work. Choice depends on the use case. Quad tree might be better for dynamic and memory stuff.
Got it. Now the big one, challenge 3. Managing high traffic and scale for giants like Twitter, Netflix, Google Docs. How do they handle billions of users?
It comes back to horizontal scaling and smart distribution. Horizontal scaling sharding is key. Split big databases into smaller shards, each on its own machine. Distributes data and load. Challenges or joins across shards and rebalancing data if things change. Then read replicas. Separate reads and writes. Reads go to a master DB. Reads go to multiple replica DBs that copy the master. Massively increases read capacity. Need to handle replication lag, replicas being slightly behind, and ensure read after write consistency when needed. And content delivery networks, CDNs. Essential for static assets like images, videos, cache content at edge locations globally close to users. Reduces latency, offloads origin servers. Can be push, upload once, or pull cache on demand. What about challenge 4, real-time collaboration like Google Docs? Multiple people typing at once without messing things up. The magic there is often operational transformation, OKI algorithms. They're designed specifically to handle concurrent edits from multiple users on the same document. If you and I type at the same time, OT transforms our operations so they can be applied correctly, even if they arrive out of order, preserving the intent. It resolves conflicts behind the scenes, making it feel seamless.
Okay, challenge 5. Media storage and delivery. Instagram, Netflix, huge images, videos. How do they manage that?
They need specialized approaches. Object storage, like S3, is fundamental. Stores data as objects in a flat structure, great for unstructured media, highly scalable and durable. For large files, especially video, chunking is vital. Split files into smaller chunks. Vaginal chunk, 2 MB. Helps resume uploads, only re-upload changed chunks. Netflix chunks based on scenes for better streaming. Video transcoding coding is crucial. Convert video to multiple formats and bytrates for different devices and network speeds. And finally, CDNs are used heavily to deliver that encoded video content globally with low latency.
Last one. Challenge 6. Newsfeed generation. Twitter, Instagram. How do you get updates from everyone you follow instantly?
It's a classic trade-off. 2 main models. Fan outright, push. When someone posts, push it immediately to all their followers' feeds. Pre-generates the feed.
Pros and cons.
Pro. Fast reads for users. Con. High write load for popular users. Millions of writes per post. High storage cost.
The other way.
Fan out read. Pull. When you open your feed, the system pulls posts from everyone you follow and assembles it then.
Pros and cons.
Pro. Lower write load, always fresh data. Con. Slower read times, complex real-time aggregation. In reality, most use a hybrid approach. Maybe push for active users, smaller followings, pull for others or very popular accounts. And critically, they rank the feed using signals, likes, time, etc., not just chronological. It's all about balancing performance, scale, and experience. Hashtag outro. So if we connect all this back to the bigger picture, it's clear system design is this huge, complex, constantly evolving field. We've really just scratched the surface today, looking at the fundamentals, the building blocks, the theories.
And how they solve real problems.
Exactly, how they apply to the services you use every single day.
So what does this all mean for you, our listener? It means understanding these principles, well, it's key to really grasping the digital world around you. It's the engineering marvel working silently behind the scenes.
Right. It's not just about code. It's about crafting systems that are robust, efficient, resilient, and ultimately delightful for you to use.
So think about it next time you stream a movie, send a message, search online. What system design elements, caching, load balancing, unique IDs, fault tolerance are working hardest to make that feel so seamless for you?
And maybe take it a step further. This raises an important question. In your favorite app, the one you use all the time, which principles do you think they prioritized? Was it availability over consistency for that social feed? Or absolute consistency for your banking app, even if it meant a fraction more delay? Thinking about those trade-offs gives you a whole new appreciation for the engineering we often take for granted.